So since we are talking about the properties of the determinant, and we were expanding the determinant using elementary row operations, and the first property was if we swap any two rows in the determinant, we get the negative of the determinant. And the second property now is that if any two rows or any two columns are the same in the matrix A, then its determinant is 0. Here is very short proof. Let two columns or rows of matrix A are same, then we will prove that determinant of A is 0. Okay. Since two columns or two rows are same, that means if I swap those two rows or those two columns, I will get no change. No change in the matrix. If the original matrix is A, and since it has two rows equal, if I swap those two rows, again I will get matrix A after swap also. That means after swap I will get no change, because those two rows or those two columns are equal, because we are assuming that two rows or the two columns in a matrix A are equal. So that means if I swap those two rows, I will get no change because they are same. So even after swapping, I will get the same matrix. Okay. But previous rule says if I find the determinant of A and I find the determinant of A after swapping, I will get negative. Since the then the matrix is same, only I have swapped, so by previous rule I will get negative. Since both things are same, I can write determinant of A plus determinant of A equal to 0. I will shift this term here, here I will get 0. This is 2 times the determinant of A, so I can write 2 times determinant of A is 0. Since 2 is not 0, this means determinant of A is 0. Hence, our claim is proved. Okay, what was our claim? Our claim was if any two rows or any two columns of a matrix A are same, then its determinant is 0. So I have proved by any two if any two rows or the columns are same, then determinant is 0. Okay, the next property is if we multiply the elements of any row or the column of a matrix A by a number k, then the determinant of new matrix after multiplication is obtained by multiplying the determinant of A by k. Okay, what it says if you have a matrix A, okay, and what do? You multiply its any row or column by some constant k. Suppose you have a matrix A here. I will do it 3 by 3 matrix. A11, A12, A13, A31, 32, A33. So this is the matrix. And what is this property? This property says if you multiply the elements of a row or the column by k, suppose k is the number, you multiply any row or any column by k. Okay, for example, you multiply this row by k. Okay, So, for example, new matrix B is obtained by multiplying the first row by k and the other rows are same. Okay, so this is the original matrix, this is the new matrix. Okay, then the determinant of new matrix, this is the new matrix, determinant of new matrix is obtained by multiplying determinant of A by K. Okay, if you take determinant of B, he says the determinant of this matrix is obtained by multiplying determinant of A by K. Okay, I mean determinant of this is equal to determinant of this times K. Okay, K times determinant of A. This is the property. Okay, okay, let's prove this property. Here is the proof. Let A is this matrix and B is a matrix obtained by multiplying row 1 by k. You can multiply any row by k, but I am multiplying row 1 by k. Then we will find the determinant of A and determinant of B, and we will prove that this thing is true. K times determinant of A is equal to determinant of B. We will prove this thing. We have to prove this thing. Okay, so we can find the determinant of this and determinant of this. Okay, let's look. Find the determinant of A by the first row. Okay, and we have many times found the determinant of A. I will just copy from above because this is the same matrix as we have discussed previously. You can check that determinant of A is this one. So I can copy this determinant because this is the same A. Okay, so determinant of this matrix A is already found. Okay, so I am just writing this determinant. Now let's check the determinant of this B. Let us expand this determinant of B by the first row. Okay, for the first row, I have negative 1 to the power 1 plus 1 times KA11. And if I ignore this and ignore this, I will have this. Okay, so I will write this determinant here. Okay, then I will go to this element. This element is A12, first row and second column. So I will write negative 1 to the power 1 plus 1, 1 plus 2, sorry, times KA12 times this matrix, this determinant, plus the last element is minus 1 to the power 1 plus 3 KA13, because this element is KA13. If I ignore this, I will get this. Okay, now once we have done with this, the first element is this one is plus because minus 1 to the power even number is plus. This one is negative because minus 1 to the power 3 is negative. This is plus again because minus 1 to the power 4, which is even number. I will have KA11 negative KA12 plus KA13. Okay, KA11 negative KA12 plus KA13, and the rest of the things are same. You can check from all of these terms K is common. So if I take K common, inside I have this thing. Okay, because this k is common, this k is also common, this k is also common. So I will have only this thing without k, only this thing without k. Okay, and you can check I have those things here without k. So since k is outside and inside thing is what? This whole thing, if you compare this with determinant of a, determinant of a is exactly this thing. A1 1 times determinant, negative A1 2 times determinant, plus A1 3 times this determinant. Okay, so this is exactly the determinant of A. So I can write this is equal to determinant of A. And on the left hand side I have determinant of B. So determinant of new matrix B is k times determinant of A. So we have proved our claim, because this is the premise of this theorem, because we had to prove determinant of new matrix is k times determinant of A. So what is this property? This means if I have a matrix, whenever I have a matrix, I multiply its any row or column by a number k, I will get a new matrix. That new matrix has the determinant equals k times the previous, the old matrix determinant. Okay.